Competency number 3. Objective. After completing this competency, the student will be able to write the rate of reaction as a function of conversion for both liquid phase and gas phase reactant systems. This competency will cover the rate laws, the relative rates of reaction, the reaction order, the power law models and elementary rate laws, the reversible reactions, the reaction rate constant, stoichiometry, batch system and his equations, and flow system and his equations. Attention gathering. In competency 2, we show that if we had the rate of reaction as a function of conversion, that means Ra equal function of x, we could calculate the reactor volumes necessary to achieve a specified conversion for flow system and the time to achieve a given conversion in a batch system. Rate laws. Basic definitions. A homogeneous reaction is one that involves only one phase. A heterogeneous reaction involves more than one phase, and the reaction usually occurs at the interface between the phases. An irreversible reaction is one that proceeds in only one direction and continues in that direction until the reactants are exhausted. It behaves as if no equilibrium condition exists. On the other hand, a reversible reaction is the one that can proceed in either direction depending on the concentration of reactants and products relative to the corresponding equilibrium concentrations. The molecularity of a reaction is the number of atoms, ions, or molecules involving or colliding in a reaction step. So, a unimolecular reaction is one in which one atom or molecule collides in any reaction step. A bimolecular reaction involves two ions, atoms, or molecules colliding, and a thermomolecular reaction involves three atoms, ions, or molecules colliding. And here we have some examples. By example, the unimolecular reaction of uranium to form thorium and helium, in which the rate of disappearance of uranium U is given by the rate law minus Ru is equal to K concentration of U. The true bimolecular reactions that exist are reactions involving free radicals, such as bromine radical plus ethane to give us bromidric acid plus ethoxy radicals. This one has a rate of disappearance for bromine given by the rate law that minus the rate of bromine radical is equal to the rate constant K times the concentration of bromine free radical times the concentration of ethane. The probability of a thermomolecular reaction occurring is almost non-existent, and in most instances the reaction pathway follows a series of bimolecular reactions, as in the case of the reaction 2 of NO plus oxygen gives 2 of NO2. So the probability of a thermomolecular reaction is non-existent because by the time the third molecule is going to collide with the other two already have reacted to form some products. Relative rates of reaction. The relative rates of reaction of the various species involved in a reaction can be obtained from the ratio of stoichiometric coefficients. For example, for the reaction A plus the B divided by A times B gives C divided by A times C plus D divided by A times D. Remember that the lowercase letters are the stoichiometric coefficients and the capital letters are the reactants of substances. We see that for every mole of A that is consumed, C divided by A moles of C appear. In other words, the rate of formation of C is equal C divided by A, the rate of disappearance of A, and C divided by A are the stoichiometric coefficients of C divided by the stoichiometric coefficients of A. Then we will have that the rate of C is equal to C divided by A times minus the rate of A, which is equal to minus C divided by A times the rate of A. So then we will have that minus the rate of A divided by his coefficient A is equal to minus the rate of B divided by his coefficient B is equal to the rate of C divided by his coefficient C and is equal to the rate of D divided by his coefficient D. We can see here that for A and B, the sign is negative because they are the reactants and they are disappearing, and for C and D, the rates are positive because they are the products and they are being formed. So we will have that the rate of A divided by minus the stoichiometric coefficients of A is equal to the rate of B divided by minus the stoichiometric coefficient of B, and this is equal to the rate of C divided by the stoichiometric coefficient of C, and this is equal to the rate of D divided by stoichiometric coefficient of D. For example, in the reversible reaction of 2NO plus oxygen will give us 2NO2, we have that the rate of NO divided by his stoichiometric coefficient, which is minus 2 because NO is disappearing, is equal to the rate of oxygen divided by minus 1 because minus 1 is the stoichiometric coefficient for oxygen. And this is equal to the rate of NO2 divided by his stoichiometric coefficient, which is 2. And here again, for NO and oxygen, we have the negative sign, and for NO2 the positive sign because NO2 is forming. If NO2 is formed at a rate of 4 moles per cubic meter second, then the rate of NO2 is equal to 4 moles per cubic meter second. Then the rate of formation of NO is the rate of NO is equal to minus 2 divided by 2, the rate of NO2, which is equal to minus 4 moles divided by cubic meter second. And the rate of disappearing of NO is minus RNO equal to 4 moles per cubic meter per second. And the rate of disappearing of oxygen is minus RO2 equal to minus 1 divided by minus 2 times the rate of NO2, which is equal to 2 moles per cubic meter per second.